digitalization has very powerful implications for grid architecture. And I go through these in some depth in the paper. Here I want to just highlight some concrete examples just so you can get a feel for what we mean by grid architecture. Grid architecture is basically the way that the system of systems that make up the grid relate to each other. And one of the most important characteristics of that relationship is interconnection, right? What are the physical connections between networks, and what are the physical connections between a network and a device? Interconnection is kind of the kind of important basic characteristic when we think about grid architecture. Building on interconnection is interoperability, which is the ability of a system component to interact with another system component and to retain the meaning and understanding of the data that's exchanged across that interface. And NARUC has a suite of resources for interoperability learning modules for you to use to get some background in what interoperability means in the electric context. A really concrete example is the idea of a USB standard, right? If you have a USB memory stick that you want to plug into your laptop to pull down a file so that you can put it on another machine so that you can give a presentation, say, that ability to take that file, transfer it from one computer to another computer, and to have that all happen seamlessly is a great example of interoperability. And there's a lot of important development that goes into the technology standards, the interconnection standards to enable that to happen. And interoperability really means relying on an open and non-proprietary set of industry standards for what that communication protocol looks like. And that is what enables, in so many of our internet applications, it's what enables us to connect and interconnect so seamlessly. And that is a standard that I think we should be adhering to in the electric system. And it's one of the most important pillars of a more digitized electric grid architecture. So if you have the ability to interconnect in networks and interconnect networks and devices, and you can do so through these easy interoperability standards, one of the things that evolves over time is that resources become more modular. And modular basically to me means that you have a standardization of the form of what the components look like, and that they can substitute for each other, and it's easy for you to replace them. My favorite example of this is actually not a digital example. It's the evolution of the container shipping industry in the middle of the 20th century, where we used to do kind of pack on shipping, where you have all of these different boxes and bags and different shapes and sizes of things to put on a cross ocean shipping. And the evolution of the container, the standardized container, so that you could have standardized cranes for loading and unloading ships, standardized movement of containers from transocean ships onto rail cars, and then from there, when they get closer to their destination, onto trucks. That container is an example of a modular technology that can go from the ocean shipping to the rail to the truck, and to be just moved along in that way at a much lower cost, much less waste. And that's an example of a modular architecture. And it greatly increased the amount of global shipping that happened, and vastly reduced costs. And so it's been one of the greatest contributors to our ability to have international network of markets. A more digital example is things like HDMI cables, right? If you need an HDMI cable to plug in, to connect your external monitor to your laptop, It doesn't matter who's you buy, what you buy, as long as it has that interface, then interoperability and modularity go hand in hand here. And then you can just plug the back, into the back of your monitor, plug into your laptop, and boom, you're done. It doesn't necessarily matter whose HDMI cable you buy. HDMI cables are all very substitutable for each other. The next important piece for grid architecture is the idea of open source software. And that is the integration of commercial software development with open community development. And the biggest example that we see in the modern economy of this is an operating system called Linux that you may or may not be familiar with. Linux is a very pervasive piece of open source software. Most of the kind of enterprise computing, whether it's banking or financial services or financial market platforms or Amazon, anything that you can think of that's like a big commercial enterprise operating in a communications network and on the internet, they're probably using the Linux operating system. And it's an open source software, which means anyone can contribute to the code, but there are some rules, some protocols that are used to maintain quality and to maintain transparency. But open source software is a really powerful potential contributor to getting really high quality, valuable digitalization in the energy system. The Linux Foundation, which is kind of the community of Linux developers, has a fairly new organization within it called Linux Foundation Energy. And LF Energy has been bringing together the community of people developing energy code, energy platforms that, if you contribute them to LF Energy, you're making them open source. So you're sharing the code with everyone. And that has a lot of beneficial implications, both in terms of cost, but also in terms of cybersecurity. All of these things culminate in the ability to have automation. And automation is where you can operate with minimal human intervention. In the 1980s, when we developed automatic teller machines, ATM banking was an early example of automation of things that used to require substantial human intervention. And this has actually been really beneficial for banks because now people who used to work as tellers now are working as as providing financial services, more customized financial services. And so the people who used to just be tellers, it's a job I did a couple of summers when I was in college, now are providing more valuable services directly to customers rather than just having to handle cash. A more recent development is the example of being able to automate subscribe and save shopping. So if you have a once every 3 months order that comes to you through Amazon or some other platform, you are definitely taking advantage of automation. Digitalization is also going to have some important implications for utility business models. The traditional regulated utility, as we know, is vertically integrated. So you have multiple transactions from generation to transmission to distribution to retail, all integrated within a single firm. One of the reasons vertical integration exists is because of transaction costs. And this is an insight that we got from the famous work of the Nobel laureate economist Ronald Coase, who as early as 1937 argued that firms exist because there are transaction costs. And because it's costly to transact in markets, that's one reason why you see this vertical integration arise. So what happens when you have technological change that reduces transaction costs? Digitalization is that move. Digital technologies are first and foremost transaction cost reducers. And so I think that's one of the most important insights that we can gain from thinking about utility business models and digitalization is that digital technologies reduce transaction costs and make it cheaper and easier for people to transact in markets. And so when that happens, it means that efficiency, if we have a drive towards efficiency, towards reducing waste, towards using fewer resources, that more transactions should be completed through markets that used to be more economically done through vertically integrated firms. So you would expect, in a period of digitalization, you would expect to see changes in the utility business model to reflect the fact that digitalization reduces transaction costs. And so this implies that things like third-party participation and markets and retail competition can yield economic and environmental benefits, particularly in this new high DER environment that we're going into in the mid-21st century. Another important implication that's of digital technologies and changing architectures is that the role of the utility can evolve into a distribution system operator platform model, or a DSO. And this is something that we see quite a bit in Europe, and it's something that I go into in some detail in the paper and give you some citations and references, because there are many different ways you can think about or model a DSO and what kind of functions that would be in the utility. And this schematic just gives you one example that you can think about, but the paper has a more detailed discussion